Assalamualaikum and good morning everyone. Today we are going to learn chapter 1, which is mass transfer basic principles on diffusion and application. Right? And this is the topic outcome from this chapter, where at the end of this chapter you must be able to define and explain the basic concept of mass transfer, and you have to know how to derive the Fick's law equation and also to calculate the mass transfer rate based on unimolecular diffusion and equimolar quantity diffusion. And also we will learn about two cases for this diffusion theory, which is equimolar quantity diffusion and one component diffusion. So these are the thing that we will learn in this chapter, which is principles of diffusion, Fick's law, and some of the application of several cases in diffusion theory. Some of the introduction in this chapter, where you have to know that what is the meaning of the mass transfer itself. So mass transfer is the mass in transit due to the species concentration gradient in the mixture, which means that in every mass transfer there must be a gradient, or we call it as driving force. So then the mass will be transferred from one point to another point until it reach equilibrium state, which means that there is no differences in the gradient or the concentration or also partial pressure for the two component itself. Like I said before, mass transfer by ordinary molecule diffusion occurs because of the driving force for the transfer, and the mass transfer rate is proportional to the area, because if we see the unit of the flux itself, it is kg mole or k mole per sm square. So it is what is the mole over unit time, per unit time, and also per unit area. And mass transfer will stop when the concentration is uniform. So this is the diagram that show you the direction of the movement of the molecule from one point to another point, where at this point it is highly concentrated with this molecule, and this high concentration of molecules will move towards the low concentration of region or molecules. And for this kind of animation, it shows that at the first box is for unimolecular diffusion, and this is the multimolecular diffusion, where at this point it is really high concentration of these molecules, and it is separated by this barrier, and this, whenever the barrier is removed, the higher concentration of molecules will move towards the lower concentration of molecules until it is uniformly distributed, which means that there is no net transfers between one point to another point. Okay, to make you more understand about this kind of theory, let's say we will have two components in a beaker which has been separated by a barrier. So at this point it is highly concentrated with component A. At this point it is highly concentrated with component B. For example, this is one point, this is a second point. So high concentration of A will move towards the low concentration of A, which is at point 2, whereas the high concentration of B at point 2 will move towards the low concentration of B at point 1 until the molecules A and B are uniformly distributed. We call it also equilibrium state. So then there is no net transfer between A and B anymore. Some of the daily application about mass transfer, which are drop of liquid dye. For example, you have syrup liquid and you have water. So high concentration of syrup liquid will diffuse into lower concentration region of syrup liquid, which is in water, until it uniformly distributed in this water. So then you will have syrup syrup in water, and then sprayed air freshener. So this kind of application is like different partial pressure. So in this air freshener there is high partial pressure, and this high partial pressure will move to lower partial pressure, which is in our environment, shoes odors, and also dissolving sugar in water. Okay, so we look over a video about how sugar molecule dissolve in water. Okay. So if you see over here, this is the sugar molecules, which is really high concentrated in these sugar molecules, and outside is the water molecules, where the sugar molecules is like the crystalline structure. It will diffuse from higher concentration region to lower concentration region in random molecular path until this high concentration region will dissolve in lower concentration region. We call it as randomly distributed until it reach equilibrium state, or we call it as steady state. Okay. Another application in mass transfer, like liquid in an open pail of water evaporates into still air, a piece of sugar. This one is like the same example previously, and also in the fermentation fermentation process, where nutrient and nitrogen dissolve in the microorganism, and many more. In our body system also will have mass transfer application, where outside of our lung, okay, so this at the surface of our lung, this like the barrier between environment and the blood. So we know that in the environment it contains really high concentration of oxygen, whereas in our blood it is low concentration of oxygen. So high concentration of oxygen in the environment will tend to move, or will tend to dissolve in our blood, which is low concentration of oxygen, whereas in our blood it is high concentration of carbon dioxide, and at the atmosphere or the environment it contains low carbon dioxide concentration. So the higher concentration of carbon dioxide will move out from our blood to the environment towards the low concentration of low concentration of carbon dioxide. In mass transfer, in diffusion, of course, you have to know the properties of the mixture. So what is the properties of the mixture that you should know? It is about the chemical composition, about how to convert the moles and the molecular weights, mass and mole fraction, average molecular weight, and also concentration. These are some of the definition that you should know in the mass transfer chapter. For example, molar concentration, density, molecular weight, molar flux and absolute molar flux, mass flux and absolute mass flux, and also mole fraction and mass fraction. So how to get the concentration from the ideal gas law? So as you see over here, it is ideal gas law equation, which is PV and RT. So we also can get the concentration by using ideal gas law, which by taking care of its unit, which is N over V, mole over M cube, which is the unit of the concentration. So N over V is also same with PA over RT. And how to get the mole fraction is by having the total concentration. Okay, for the molecular concentration, Ca over C total, we will get Xa. Same goes to Ya, and Ya also we can get the mole fraction for Ya, which is in gaseous form, is from Dalton's law. Okay, or we manipulate from the ideal gas law equation, where Dalton's law states that partial pressure in one component when it plus with another partial pressure of one component in a mixture, okay, they will the partial pressure for oxygen over partial pressure of mixture, we will get mole fraction for oxygen. And same goes to nitrogen. If you want YB, which is nitrogen, PB over P total, we will get YB. So this is the equation for Fick's law. So whenever you know about Fick's law, it always relate to the diffusion process. So Fick's law states JA is equals to minus C dAB dXA over dZ. So what is JA? JA is the flux, minus C. Minus is the direction of the molecules, C is the concentration, dAB is the diffusion coefficient, and normally it is constant. dXA is the mole fraction, different in mole fraction, and also dZ is the elevation or different in length. So we have two kinds of equation. Whenever the C is constant, we can reduce this equation to be like this equation. If C is constant, CA is equal to CXA. Okay, so if we want to replace this equation into the Fick's law, there is del. Alright, so we have to differentiate CXA with respect to T, and then C dXA, we take out D from CXA and differentiate with respect to X. So the remain is DCA. So we know that dCXA is equals to dCA. So you see over here, C dXA. We replace dCA into dCXA. So then this C is eliminated and this dXA is replaced with dCA, where this equation can be reduced into this equation. So both of these equation is the Fick's law equation, where if C is constant, you can use this equation, and if C is not constant, you can use in terms of mole fraction. It is same equation. Alright, and the unit of molar flux is mole per sm square, and the unit of diffusivity coefficient is cm square over s, or m2 over s. So in this slide, I want to show you how to differentiate between JA and NA. So if you see this equation, it is Fick's law equation, which is JA is equals to minus dAB dCA over dZ, where the C is constant. And if we want to convert from JA to NA, there must be some convective process which is result in the bulk flow CA times V, concentration time velocity. JA and NA is the same term, which is flux. The unit also same, but the application is different. So JA is normally used in a bulk fluid, whereas NA it has its time time frame. Okay, the velocity is average. So this is the equation for NA. NA is equals to JA plus CAV. Alright. Why we can add these two terms? It's because the unit is same. If you multiply concentration unit with the velocity, it also results unit for flux. And why we will need to add this term? Because we want average velocity in bulk motion. And then for this one is for component A, it same goes to component B, and B is equals to JB plus CBV. And we know that in every mixture, flux for A and B is equals to 0 for steady state, which is NA plus NB is equals to N. And we know that N total is CV. So if you substitute this equation, alright, substitute equation 4 into 5, okay, you will get this equation. Okay, And next, whenever you substitute equation 1 and equation 6 into equation 2, which is this equation, it will result in this equation, and also in terms of concentration. This one is in terms of mole fraction, this one is in terms of concentration.